Hello, welcome to Fermilab, to our lectures. We thank you very much for joining us tonight. I am Dave Dykstra, Chair of the Fermilab Public Lecture Committee. So now I'd like to introduce tonight's speaker, Dr. Gerald Gabrielse. Dr. Gabrielse became a professor at Northwestern University a few years ago and is the founding director of its Center for Fundamental Physics. Prior to that, for 30 years, he was a professor at Harvard University. He's a member of the National Academy of Science and the American Academy of the Arts and Sciences. He was a pioneer in the field of low energy, antiproton and antihydrogen physics research and is a world leader in that field. He was awarded Harvard's Prize for the Exemplary Teaching of Undergraduates and their Prize for Exceptional Research, along with major prizes from the US American Physical Society, from Germany, and from Italy. I have a bit of a personal connection with him myself, since we both attended the same Chicago area college, and I've heard him speak in other contexts on science and faith. But to welcome him now, everybody, please click on or touch your raise hand button, and we'll get a count of that. And go ahead, Jerry.
Well, hello, everybody. If you see where I'm sitting, I live in a state of denial. Okay, that's the building that I work in, and I've carefully removed all of the snow from the lawn so that you would think that or realize just what paradise Northwestern University is. I had hoped to do this lecture, I guess it was last spring sometime, in person, but it wasn't to be, and so we'll do the best we can via Zoom. It is a privilege to speak to you. The topic today is antimatter and deep mysteries. And as was mentioned, I'm the director of the Center for Fundamental Physics at Northwestern University. I'm also on the faculty there. And I've been there for several years, I guess, but my whole career I've been trying to study the most fundamental physics that I can. And I'll show you a path which is a little different than the Fermilab path, which is also important and which is a path that's followed by many more people than folks like me. I'll talk to you about tabletop physics. But to start out, I want to introduce you to antimatter. That's probably a bit more necessary than it used to be, because I think Star Trek is fading from many people's memories. And then after introducing antimatter, I'll talk a little bit about what the standard model of particle physics is. You can't really go to lectures at Fermilab without hearing about the standard model of particle physics, at least not scientific lectures. And I will try and explain why it's the great triumph, but also the great frustration of modern physics. And then I'll try and illustrate how one can try and learn about this standard model of particle physics and what's clearly wrong with it, probing for hints, but using a tabletop experiment. And a tabletop experiment is probably, that shouldn't be hyphenated, it's done in different ways, but a tabletop experiment is something that's roughly the scale of a tabletop rather than the scale of a very large building that requires thousands of people to work on. Okay, and to be a little crude about it, okay, and my Fermilab friends will hate me for this, but if you want to learn what's inside of a chicken, okay, one way to do it, and this is very crude, is you take two chickens and you collide them and you see what flies out. Now that's an unbelievably awful way to do it, and the image probably is scarring you even as I continue, okay? Instead, what we try and do is we try and measure, instead of using energy and just smashing things together in the way that's been so fruitful at Fermilab, what we try and do is measure with very, very precisely, but with low energy, much smaller scale experiments. We try and see small little effects that we can interpret, and I'll illustrate that. And so the kinds of illustrations I'll give are testing the most accurate predictions of this standard model. That's the fundamental mathematical theory of physical reality. Testing something that are called the symmetries of the standard model, and in particular, comparing matter and antimatter is what I'll use to illustrate. and looking where the standard model and possible improvements to the standard model that have been proposed, to look where those things agree or disagree. Okay, and okay, so let's start with what is antimatter. Now, those of you who are a little older, okay, know what antimatter is because you heard or watched Star Trek, right? So Spock and Kirk knew what antimatter was. That's well before Kirk got his CPAP machine. Okay, and there's the, you know, the starships, the spaceship Enterprise was propelled by antimatter. And when Klingons were coming, then antimatter was put into the containment pod, and sometimes the pod ruptured or threatened to do so, and that created various episodes. Dan Brown's book, there's a best-selling book and movie actually from some years ago, was actually based on my research with antimatter. Okay, and I'll discuss that a little bit as well. Now, we actually do science, not science fiction. And that's so we'll talk about what the science is behind the science is that's in front of the science fiction. So there's generations of Trekkie. There's all sorts of clever directions that show was taken. But the science reality behind the science fiction, well, what is matter? What is antimatter? Let's do a comparison here. Now, we are made of matter, okay? Matter, to be oversimplify a bit, is anything that's made out of electrons, protons, and neutrons. Now, dark matter may not be, I'll say more about that later, but the matter that we know and love is electrons, protons, and neutrons. Okay, but the electron is the very lightweight one. There's about 2,000 of them per proton, and a proton and a neutron are about the same mass. Okay, so they all have a mass, they all have a size. Well, the electron size is so small we haven't detected it yet, depending on how you define the size. And so we say it's smaller than 10 to the minus 18 meters, which is not very large. Now, those were the matter particles, and now the antimatter particles, what about those? Let's see, let me put my laser pointer on here. So these are the particles, and now for the antimatter particles, well, there's one that corresponds to each of the matter particles. So the electron is matter, there's a positron, which is antimatter, and the positron, has the opposite sign of charge, okay, but it has the same sign, the same mass. Okay, so that's the difference between the two. Okay, just the charge. The antiproton is the antimatter counterpart of the proton. It has a negative charge rather than a positive charge. It has the same size and the same mass, so far as we know. And then the neutron has the same mass as the antineutron, and it's also oppositely charged to the antineutron, but by a technicality. They both have zero charge, so negative zero is zero, so the rule still holds. Now, only measurements will tell how identical the particles really are. Okay, so in the end, this is a kind of theory, it's a model, and we always go in the sciences, we go to reality to find out whether we're right or not. Now, we can also make atoms out of matter, that you know, and we can make them out of antimatter. So in high school chemistry, you studied the simplest atom, and it was the hydrogen atom. And the hydrogen atom has a proton in the center and an electron in orbit around the outside. Now, of course, with quantum mechanics, nothing's really in orbit, and there's no angular momentum, and this is fuzzed out and all this kind of stuff. I love quantum mechanics, but we don't have time to go into the details. That would be a fun other lecture, but we won't do that tonight. Okay, now an antihydrogen atom has an antiproton with a positron in orbit. Okay, and otherwise it's the same. Well, it's completely different because there's different particles, but it has the same structure, we believe. Now notice, this atom, the hydrogen atom, is held together because there's a proton attracted to the electron. They're opposite signs of charge, and opposite sides of charge attract each other. Similarly, for an antihydrogen atom, there's an opposite sign of charge, a negative nucleus and a positive electron, and they attract each other as well. So that works also. Now, of course, if we can make atoms, we can out of antimatter, we can immediately think, why not make people out of antimatter? And if we can make people out of antimatter, why not make an antimatter universe? So if we have matter particles, we can make matter molecules and atoms, and matter cells and matter people. If we have antimatter particles, we can make antimatter atoms and molecules, antimatter cells, and antimatter people. And the interesting thing is we currently do not know any reason why people and a universe could not be made out of antimatter rather than matter. That's what I'll refer to as the four mysteries that I'm going to discuss, deep mysteries as I called them. Now, would antimatter and matter people, I have a typo here, would matter and antimatter people differ? Okay, so let's consider Gabrielse made out of matter. Okay, there's me in an uncharacteristic pose wearing a suit. Okay, and we could ask, suppose we could take all of my particles, all of my protons, electrons, and neutrons, and turn them into antiprotons, anti-electrons called positrons, and antineutrons. What would happen? Okay, would I be smarter? That'd be good. Would I be more handsome? Would I be less massive? All of those things would be great news. Okay, unfortunately, the bad news is that modern physics predicts that Gabrielse and the antimatter Gabrielse would be just the same. It's very difficult, in fact, it would be to tell the difference between the two. Now, insofar as we know, it's not only people, but the whole universe could have been made out of antimatter. In fact, it would be nearly impossible to tell if we lived in a universe made out of antimatter rather than matter. The only known differences would be so tiny that very huge accelerators like at Fermilab or CERN would be needed to tell the difference. So, deep mystery number one, why are people and the universe made out of matter and not antimatter? And as advanced as we are in physics, we do not know the answer. We are still now looking for clues by comparing antimatter and matter for some possible differences that we've missed. Okay, what happens when antimatter and matter meet? This is key to the science fiction, okay? And that's why there's so much fascination in science fiction with antimatter. And the word that's used is annihilation, which of course adds to the intrigue. On the particle scale, here's what happened. If I have a matter particle called an electron, and it collides with an antimatter particle called a positron. Okay, we've gone through those already, and they hit each other. They are attracted because they have opposite signs of charge, so they're quite willing to hit each other. Both particles will disappear entirely. We say they annihilate, and when they annihilate, energy is released. And if for different annihilations, the energy is released in different forms. But here's one way to think about it. If this was in a bucket, okay, and this collision happened and the annihilation happened, what would happen afterwards is you would have a hotter bucket. Okay, there would be a little bit of heat given off by this annihilation. Okay, a little bit of heat energy, and it would heat your bucket. Now, the energy that's released, you all know the formula that applies to it, because almost everybody in our culture knows E equals mc squared. That's Einstein's famous formula. Now, more people know the formula than know what it means, so I'm going to try and explain what it means in this context. To do so, let's ask the question, what happens when antimatter and matter Gabrielse meet? So here's the anti-Gabrielse and here's the Gabrielse, and they're about to shake hands, okay? Now, this word annihilation is going to appear somehow. What's the story on that? Well, let's suppose I'm 100 kilograms, the anti-Gabrielse is 100 kilograms, and the Gabrielse is 100 kilograms, because after all, we're identical, except for having matter change to antimatter. And since all the matter particles have the same mass, it's reasonable to assume that the Gabriels and the anti-Gabriels, will have the same mass. So in Einstein's famous formula, the E is the energy that would be released, okay, and M will be the mass that disappears, which will be all the mass, assuming that all the protons find all the antiprotons and annihilate, all the neutrons find the antineutrons, and we'll just assume that for simplicity. There may be a bit of an ignition problem here, but we won't go into that because this is a conceptual discussion. And the energy released and the mass that disappears is related by the speed of light. Who would have expected that? Okay, that's why we needed Einstein to tell us this, because that's quite a jump. Now, if we say how much energy is for 200 kilograms of mass, that's one overlarge, male adult. Okay, how much energy is released? Well, I wrote it in different units here. I hope I've calculated it correctly. But there's this many kilowatt hours. We pay our bill, our electric bill in kilowatt hours. Okay, and a kilowatt hour, well, a typical house will take about 20 kilowatt hours per day, okay, of power. So you can see this would give electricity for lots of houses, okay? Or in terms of the yearly output of 500 nuclear power plants, and you can see the scale, because a nuclear power plant, gives electrical power to a whole region of the country. Or if you like to have violent tendencies, it's the energy from 4,200 megatons of TNT. Now, a modern missile can carry about 20 megatons, I'm told. I'm not expert in this, okay? But, this is the, one person, one matter and one antimatter person converting their mass to energy would release an enormous and unthinkable amount of energy. Way more, thousands of times more, about 1,000 times more than a nuclear explosion per unit fuel mass. Okay, now one could worry about having too much antimatter around. More about that in a moment. So let's ask, how much antimatter is there in our universe? Well, the answer is essentially none. Okay, there's a few positrons that emerge when nuclei decay. Now, these radioactive nuclei are still remnants of the Big Bang. They haven't yet decayed because they have long lifetimes. Okay, these positrons are used in positron imaging tomography. They're very useful. And we use such positrons at Northwestern. We compare them with electrons as a way of studying the symmetry between matter and antimatter. Another way to do it is done both at Fermilab and at CERN. And I put a picture of CERN because it's further away and because I worked there, okay, for 30 years. I led a team at CERN using antiprotons. But here's France over here, and here's Switzerland with a medium-sized airport, the world's largest storage ring, a big circular tunnel that's 16.6 miles in circumference there, and antiprotons and protons were at one time put into there to collide with each other and make some Nobel Prizes, okay? But the antiprotons were actually made in a smaller ring, okay, in this part of the site. But that's one way to do it. It takes a lot of energy and a lot of people to do this. So relatively speaking, compared to the number of the protons in the universe, there's almost no antiprotons. Also, a very few antiparticles are produced when particles from space smash into atoms in our atmosphere, okay, but that's also a very rare event. And there are some positrons that have been detected annihilating near the center of our galaxy. So there's almost no antimatter in our universe, and we either have to get it from a radioactive source or we have to smash protons together at tremendously high energy. Actually, this should say smash protons and protons together at Fermilab or CERN, another typo, okay? Sorry, made the slides today. All right, now a best-selling book was based on our work. What we did is we went to CERN and we trapped antiprotons in a small container called the trap, and I'll tell you about such a trap in a few moments, okay? But this, apparently this author, Dan Brown, heard about this. And in his book, and then in the movie, thugs stole the trapped antimatter from the CERN lab where we did the research. They buried the trapped antimatter under the Vatican, and then they threatened to let it annihilate, let it fall out of the trap, annihilate with protons. And since they knew about the explosive power, the cardinals were really scared as they met to choose a new pope. Okay, so that was the premise of the book. There was one small missing detail, okay, and the missing detail is if all the antiprotons ever made in the history of the world were annihilated at the same time, there's far fewer than there would have been in the Antimatter Gabrielse, there wouldn't have been enough energy to boil a pot of tea. So clearly the cardinals should have studied more science before they got all upset and then made the movie. But I always say that what Dan Brown did for the Roman Catholic Church in the Da Vinci Code, he did for my antimatter research in angels and demons. Okay, whenever antimatter comes up, people ask, what about antimatter weapons then? Could we blow up something? That seems to be a human thing to think about. And the reason is there's much more explosive power than nuclear weapons with the same mass. But I've already hinted at some of the problems. We simply do not know how to make large amounts of antimatter. No one has figured that out or even come close. Remember the illustration that if we took all the antimatter ever made and annihilated it at the same time, we still wouldn't have enough, to heat a cup of tea, a pot of tea. It takes a tremendous amount of energy to produce antimatter. It's almost impossible to store it because you have to have a container where the antimatter doesn't hit the walls. More about that in a moment. Now that has a disarmament opportunity, of course, because if you did manage to make a weapon, the person most likely to be destroyed would be the weapon's owner. So that's a nice feature, but the rest make it kind of difficult. I'm often asked, can you make an antimatter energy source? Well, the answer is no, again, because storage is essentially impossible, okay? And it takes much more energy to produce the energy than is released, okay, by many factors. And one thing to remember is that when we produce energy from fossil fuel or from uranium, in both cases, our Earth has prepared limited supplies of these fuels, and they're buried in our Earth, and we dig them up and use them up once for all time, okay? And that makes it possible for us to do it. If we had to take, organic matter and turn it into fuel oil, that would also be a very time-consuming and energy-intensive process. And I don't even know how we would make uranium, and we'd have to use accelerators again. It would be very inefficient, take much more energy than we could ever get from it. So, okay, now let's change to the pure science. Get to the standard model and the deep mysteries. So, what is the standard model of particle physics? I'll try and give a brief explanation. Then deep mysteries and antimatter. There are some deep mysteries that are directly related to antimatter. And then I'll just mention other deep mysteries just for general interest. Okay, now the standard model is the fundamental, it's the most fundamental mathematical description of physical reality, okay? And I call it the great triumph and the great frustration of modern physics. And I'll explain why. First, what is the standard model? Well, it's a postulated set of standard particles, okay? There's quarks, okay? And there's leptons, okay? And there's neutrinos, and then there's various glue particles, some called gluons, some called photons. These are also light particles that we see, and Z bosons and W bosons, and then the Higgs boson, which gives us a way to discuss particles giving mass in kind of a unified way. All right, so there's this collection of particles, and each of these particles also has an antiparticle. Okay, so it's a pretty large set. So it's much larger than just proton, neutron, and electron that we started with. More about that in a moment. So the Standard Model is this collection of particles. It's a collection of interactions. These particles interact in different ways. Okay, they interact electromagnetically. Okay, like charges repel each other and opposite charges attract. They attract gravitationally, but that's very weak, but it's strong enough that it holds us to Earth, which is a good thing. And they also interact inside of our nucleus in a very strong way, strong enough to overcome the interaction of the charges. So our nuclei, which are all positively charged, don't blow apart. If you think about that, all those positive charges are crammed together. That's a little unstable, but fortunately, there's what we call the strong force, which overcomes that. It holds our nuclei together. And then there's a weak force, okay, that causes nuclei to decay. So there's a collection of particles and antiparticles. There's these 4 types of interactions, and there's something called symmetry. And I don't really have time to talk about symmetries so much, though I would like to. I'll give you the names. They usually have these initials. There's charge conjugation. That's a symmetry where you turn particles into antiparticles. There's parity, which is reflecting some sort of physical experiment in a mirror, basically. And then if you have parity symmetry, the experiment you see, if you build an experiment that looks just like the experiment in the mirror, it will have the mirror outcome. And then there's time reversal symmetry, which catches people's fancy. I was once on NPR, and there was a theorist talking about clocks running backwards and all this sort of thing. That's not really what happens. Time is a parameter in a lot of our physics theories, and it turns out the equations we develop will describe a different set of circumstances. If you substitute for time, you substitute the negative of time. And I don't really have time to talk about that. But these 2 combinations of symmetries called CP and CPT, applying all 3 of these symmetries together, are really the symmetries that turn matter into antimatter in the most important way for fundamental physics. And then this whole Standard Model is stitched together with a highly mathematical framework, which is called quantum field theory. And out of quantum field theory comes some invariances. Again, I won't talk about this, but I think the idea to take away from this, if you're not already acquainted with this, is there are particles and antiparticles, there are interactions, and there are ways that certain of these particles relate to others, those we call symmetries, and then there's a mathematical framework called quantum field theory. Now, I started the lecture with electrons, protons, and neutrons, and the electron is in fact here on this standard particle chart, but the proton and the neutron are not. Okay, so what's going on here? Well, here's the standard particles, and here's the electron, the proton, and the neutron, and their antiparticles. And this the sketch below represents the relationship. The proton is actually made of an up quark. This is one of the quarks, another up quark, and a down quark. Okay, and you put those 3 quarks together with lots of glue. Well, we call the glue that holds them together gluons. That's another kind of particle. So you put an up quark, a down quark, and you stir in as many gluons as you need, and then you make a proton. And if for an antiproton, that's an anti-up quark. So it's an anti-quark, another anti-up quark, and an anti-down quark. And a similar sort of thing happens with the neutrons. So electrons are fundamental particles. Protons are elementary particles. Protons and neutrons are not really elementary particles because they have other stuff inside. If the electron has other particles inside, we have so far failed to detect those. Now, the great triumph of the Standard Model. Let's start with that and then go to the great frustration of the Standard Model. In my lab, we've been able to measure the size of the magnet in the electron. So every little particle, electron particle, acts like a magnet. And here is the size. The details of this aren't so important. What I'm pointing to you is the number of digits that we know this to. Okay, there's lots of digits here. We know this to 3 parts in 10 to the 13. Now that's a ridiculous precision. You know, almost no measurements in physics are ever made at this sort of precision. Okay, this is the most precisely measured property of an elementary particle. More about that in a moment. Now, the electron isn't really a bar magnet. There's no north and south pole inside because there aren't any magnetic charges that we've ever detected in reality. But it turns out if you have a little current loop, a little loop of charge turning in a circle, an electron has charge and maybe it's rotating, then you do get, it does act like a little bit of a magnet, okay? But you really have to use quantum mechanics to describe electrons. And it's kind of strange to make these pictures, even though it makes it a little bit more intuitively accessible, because an electron, if it has no size, it's a bit mysterious how it could have a current loop, right? Because if it had no size, the current loop would have no radius, so there would be no magnet, okay? And also an electron doesn't rotate, even though it has spin. But that you really have to take a quantum mechanics course to begin to understand. Well, you don't really understand it, I would say. You learn to accept it, okay? It's just the mystery of quantum mechanics. Now, we measure the size of the magnet in the electron to a ridiculous precision, okay? And the Standard Model's greatest triumph is predicting what we measure to 1 part in 10 to the 12. That's a remarkably, remarkably accurate prediction, okay? I'll show you later how that prediction is made, but again, it's an exquisite precision. It's the most precise prediction of the Standard Model, and it's the most precise confrontation ever made of theory and measurement. And of course, we made the measurement just to test the Standard Model, okay? Because we know the Standard Model, is not right, okay? And yet, well, more about that, okay? So now the other triumph of the Standard Model predictions is that it's consistent with all measurements made to test the Standard Model so far. Okay, so that's a pretty good track record because there's a sizable community of people trying to test the Standard Model. Now, the great frustration is that the Standard Model cannot predict basic features of our universe. I already mentioned Deep Mystery 1. Why is the universe made out of matter rather than antimatter? In science, we always look for explanations to these sort of things. We don't like the explanation so well because it is. We always try and find some way to explain it in terms of something similar. So far, we haven't been able to do that with the Standard Model. So physicists tend to think that there's got to be a reason that a matter universe is more likely than one made out of antimatter. But it's something that there must be something we don't understand about differences between antimatter and matter. Deep mystery number 2, I will go over in the next couple of slides. How can a universe exist at all following the Big Bang? You know, why did the matter and antimatter not annihilate? Okay, and the universe basically should not exist according to the Standard Model as we currently understand it. And so let's take a closer look at that. A Big Bang is, we observe that all the stars are rushing away from us, and we extrapolate back to a time when there was an initial Big Bang. Everything was exceedingly hot at that point, and space-time was completely warped and all those interesting things that we don't really have time to go into right now. But after the Big Bang, in the Big Bang, according to the Standard Model, essentially equal amounts of matter and antimatter would be created during this hot time, okay? And so if you have equal amounts of matter and antimatter, it doesn't annihilate right away because it's moving so rapidly that the particles don't have any interaction time. But as the universe cools, the antimatter and the matter would find each other eventually. They would collide, and then they would annihilate. And if there's equal amounts of matter and antimatter over billions of years as the universe cools, we might expect that the matter and antimatter would all annihilate, and there's equal amounts, so there's nothing left. So those are pretty big questions. How did the matter survive? How did any matter survive at all? And how is it that we exist? Again, the conclusion is there must be something we do not understand about the difference between antimatter and matter. Now, I'll mention two other mysteries, numbers 3 and 4. These aren't specific to antimatter, but you may have heard these, and I think they're worthy of mention. We do not currently understand most of what makes up the universe. Okay, and so most of the universe is made out of dark matter, which we know is there because of the way galaxies move. There has to be something there if our theory of gravity is right. Okay, and yet we can't find it so far, but a lot of us are looking. And most of the energy in the universe we don't understand at all. The universe is expanding more rapidly. So this is sort of depressing that we have these really big mysteries yet in physics. Or you can say it's exciting, or if you're an old or young person, you can say there's job security for physicists because most of the universe we have yet to understand. Okay, so what have we discussed so far? We've discussed what is antimatter, what is the standard model, how can the standard model predict what we measure so accurately and yet not account for basic features of the universe. And so we've concluded there must be something we do not understand, something significant, in fact, we do not understand about the differences between antimatter and matter. In the following minutes of my talk, the last section, I'm going to talk about experiments that can be done to find hints about what is missing. Okay, so to find hints of what is missing, we need measurements. And the measurements I'll illustrate come in 3 forms. One is we want to test the standard model's most precise predictions as accurately as we can. Our electron magnetic moment measurement does that already. We want to test the symmetry of the standard model that relate matter and antimatter, so directly compare them. And we want to test where the standard model and possible improvements to the standard model make different predictions. Okay, just a quick aside. What difference will it make if we solve the antimatter mysteries? There's no evident practical use for these, and I'm always asked this when I give popular lectures, so I'll just tackle it straight on. Okay, and the implied question is, does it make enough difference that the US should provide finances from taxes for such pure science with no evident practical use? And I'm going to give 2 answers to that question. One is the science answer. If we find a solution to these mysteries, and if this changes our fundamental description of reality, then big consequences typically result if we look back in history. For example, before the discovery of quantum mechanics, scientists were quite satisfied with what is now the high school physics description we call classical physics. But now we know about quantum mechanics, and countless quantum devices are common and have revolutionized not only science, but our whole culture. The societal answer is pure science provides new possibilities for a technological society. Oh, another typo, society. Some of us do not worry much about applications. We do pure science. Nonetheless, pure scientists discover and invent things. For example, atomic clocks led to the GPS system. This was not envisioned at all when the atomic clocks were invented. Scientists were trying to have better timing for their experiments. Nuclear magnetic resonance led to MRI imaging. One of the inventors of nuclear magnetic resonance told the reporter there were no applications for this. It was esoteric, okay? He didn't envision that every hospital would have as many MRI imaging machines as they could afford, because you can look inside of people without taking them apart. Transistor was developed by scientists who were not trying to make a computer and a cell phone. That wasn't what they were imagining at the time. The laser was invented to make a better light source, not imagining that CD players, communications, grocery store checkout and so on would all rely on lasers. The internet was invented essentially at CERN, okay, to handle transfer of information. I invented a self-shielding solenoid, okay, because the subway was too close to my experiments, and it's now in MRI imaging machines because they can locate these closer to elevators. The point here is that science discoveries and methods allow and fuel the continuing development of a technological society. Okay, now I want to give some examples of tabletop measurements, okay, that seek answers to these deep mysteries, especially the ones having to do with matter and antimatter. And I'll use examples from my research group because I have better pictures and I know these well, but there are many other examples that could be done. I'll give one example of testing the standard model's most precise prediction. This one I've mentioned already, the magnet in a single electron, but I'll show you what the apparatus looks like and say a little bit more about it. And then to test the symmetries of the standard model that relate matter and antimatter, we compare the measured electron and positron magnet. So these two are related. They use basically the same apparatus, except in one case, we put an electron in it, one electron that we hold for months at a time, in fact. And for this experiment, we'll put in a positron that we'll hold for months at a time. And then a third class of experiments is to test where the standard model and possible improvements disagree. Okay, and I'll use the Acme measurement of the shape of the electron charge. It's called an electric dipole moment. Now, my Center for Fundamental Physics was set up just to do these sorts of tabletop measurements. If you search on the web, you can find an article about that, and I won't say anything about that. Okay, so let's do the electron and positron magnetic moment measurements. These are the folks who are working with me. We're also lucky of late to have some Fermilab collaborators who are helping us devise a future generation, which will be better. But here's the standard model's prediction, very mathematical. You have to do 12-dimensional integrals. You have to do, sort of like 13,000 of these integrals. It's highly mathematical. I won't talk about it, but that's what the standard model theorists do, and they make these predictions. And until very recently, our measurement was agreeing with the best standard model prediction. But the standard model prediction uses something called the fine structure constant as an input that has to be measured. And when that was measured about 2 years ago, then this discrepancy appeared, and a lot of theorists wrote papers about what may be causing that. Very recently, though, another measurement of the fine structure constant came out, and the prediction using that fine structure constant puts us over here. So I would say things are a little murky right now. So for now, the fact that it gets within parts in 10 to the 12th is the great triumph that I mentioned before. Now, how do you hold an antimatter particle? You can't put a positron in a bottle, right? Because the positron will annihilate when it hits electrons in the bottle. So you need a bottle that has no walls. Okay, that's called the particle trap. And here's the physics you have to know. If you take a magnetic field, directed along this direction. So if I had a horseshoe magnet, I would have the horseshoe looking like this. Okay, and there's a magnetic field there. And a charge in a magnetic field goes in a circle. So here's a negative electron, for example, going in a circle. And since opposite charges repel, this negative electron is repelled from the charges we put above and below, and so it stays stuck in between. It's in a particle trap, and we actually hold particles for months and months at a time, just one at a time, doing that. And then this is what an accelerator is, okay? It's really big, so the magnets are expensive, so they put a hole in the middle and put little magnets all the way around. But we don't do that either. What we do is we cool the particle down so much that we see the quantum structure in its cyclotron motion. So this becomes a homemade atom when it's very cold. And we see energy levels just like in an atom, the way you learned in high school chemistry. And you have to cool it down, in our case, to 1/10 of a degree above absolute zero. And I don't have time to explain that right now, but just to give you the feel for what's involved, you get wave functions that are pictured there in one state and the other, and we put photons in and make the state jump back and forth. Okay, but it's a homemade atom. There's these energy levels, and we just measure the energy it takes, the light energy that we have to put in to make these transitions. It's a kind of spectroscopy. And then we use lots of quantum tricks that I don't have time to talk about. Here's the scale of it. We call it tabletop physics, but you need a pretty sturdy table to put this on it. So we put it on the floor. Okay, but this is the size of the device that makes the strong magnetic field. The magnetic field is so strong that if you drop a screwdriver inside the bore of this, there's a hollow bore inside that you can't see. If you drop a screwdriver inside, you won't have enough strength to pull it out. It's at 6 Tesla. Okay, here's a picture of the insides. There's lots of electrodes, lots of machining. The particle sits way inside of this centimeter type cavity. Okay, so there's lots of engineering that has to go into this. We're now using superconducting quantum interference devices to detect these motions. That's a promising new direction. Okay, and so on. So I just wanted to give you a little bit of a feel for what's involved in doing such an experiment. Now let me switch gears. Well, let me just say we could put a positron or an electron in this apparatus and use these methods. And by comparing the magnet of the positron and the magnet of the electron, we could test the matter-antimatter symmetry of the standard model, way more precisely than anyone else can do with what's called the lepton particle. Okay, now another question is, how spherical is the electron charge? Now, in order to do this measurement, we have to make an entirely different experiment, entirely different apparatus. We actually use molecules for reasons I'll say in just a moment. But for those of you who know the buzzwords, we don't say how spherical is the electron charge, so that's really what we mean. We say we're measuring the electric dipole moment of the electron. Does the electron have a little bit of more of its charge on one end of it than the other? Now that's a weird question, because if we believe the electron has no size, how can more charge be on one end than the other? But okay, that's a classical question and we have to answer it quantum mechanically, so I'm cheating a bit. Now there's all sorts of predictions of what size electric dipole moment, what size of departure from sphericalness we should see. Okay, and so these are all the predictions. So this is a case where there are alternatives to the standard model. Okay, and the standard model says that there should be an electric dipole moment, that the electron charge should not be quite spherical. But notice that my scale is broken, okay, and it jumps by some 5 orders of magnitude here. So it's orders of magnitude smaller than we could hope to measure using the methods that we've dreamed up so far. Okay, and our first measurement, okay, brought us this far, and our second measurement brought us this far, and now we're making a third generation where we haven't eliminated all these theoretical possibilities or discovered the electric dipole moment yet, but we're still hopeful of doing so. Here's another way to do it. There's no possible way to understand it unless you do going in. But what we do is, for certain kinds of particles called supersymmetric particles, we're able to set limits which are of much higher energy than even the LHC can set, okay? So even though these particles are done at very low energies, they can set what are considered in physics very high energy limits, but I don't have time to explain that. Now, this experiment is done by a team. It was 2 of us at Harvard to start, John Doyle's group and my group at Harvard. When I moved to Northwestern, then we moved. And then our Yale collaborator, David DeMille, recently moved to the University of Chicago. The result is the new generation, the all new apparatus is being built up at Northwestern. It's moving. Okay, here's the history of measuring the size of this departure from sphericity. The absolute numbers don't matter very much. Here's one measurement. It was consistent with 0. Here's another measurement we made. Someone else made a measurement in between. Okay, and so far we haven't yet detected any departure from sphericity. That means so far the standard model seems to be correct, not some of these proposed improvements. Now, in order to do this, we have about 10 lasers operating all the time. One big laser makes some molecules come out. It's a process called ablation. Those molecules move through a region here. We excite them with lasers. We detect them with lasers. We apply electric fields. We apply magnetic fields. We apply more lasers. We steer them in our new generation with an electrostatic lens. Again, the details aren't so important. And if you look at the real apparatus, we're straining the notion of a tabletop a little bit because we have several tabletops, laser tables that are just covered with lasers and optics. In the new measurement, we're making a big shielded box. It's bigger than our previous one. It's about 2.2 meters long, several yards long, and about 1.5 meters high. Okay, and that is those parts are just ordered. We don't have engineers because we're just tabletop physicists. And so unlike at Fermilab, we're not privileged to work with engineers. So we do our own calculation. I really enjoy this picture that one of my students gave me of the mechanical vibrations of our new vacuum chamber. As you might expect, this is slightly exaggerated, maybe hugely exaggerated, but the picture I thought was hilarious. The thought of our delicate apparatus shaking around like that when you vibrate it. Okay, we're projecting for our new measurement to maybe improve things by more than an order of magnitude, another factor of 30. The details of this are not so important. I'm just, again, trying to give you the idea. Okay, let me conclude as I started. What I've tried to tell you about and give you a feel for is what is antimatter and how it's related to some deep mysteries that are really nagging mysteries that physicists strongly want to solve, okay? I explained what antimatter is, the antimatter counterparts of matter. We discussed the standard model of particle physics, the collection of particles and antiparticles. Okay, the interactions of these, the symmetries that they have, matter to antimatter, for example, and the mathematics that holds it all together. And the standard model is the great triumph because it can predict things, predict physical quantities that we measure to a remarkable precision. And it's the great frustration. We know it has to be wrong or have missing elements because it can't explain some of the most basic features of the universe, like, for example, why we have a universe at all, why it didn't all annihilate after the Big Bang, and why the universe is made out of matter rather than antimatter, as experiments tell us. And then I tried to illustrate, just to give you a flavor of what the tabletop probes that we use to get hints as to what is wrong or missing from the standard model. One class of such measurements is testing the most accurate predictions of the standard model. There, the prototype example is the magnetism of the electron, which can be calculated by the standard model much more accurately than any other quantity, and we can measure it much more accurately than any other property of an elementary particle. We can test the symmetries. We can do that by comparing the magnet in the electron, which is made of matter, and the magnet in the positron, the anti-electron, which is made out of antimatter. And so that will hopefully we find a difference. That would be great, aside from the obvious sign that's predicted by the standard model, but we'll see. And then with the electron-electric dipole moment measurement, is the electron spherical? There we're looking where the standard model and possible improvements disagree. And I didn't discuss it very much, but we actually use very different methods where we use molecules because there's a huge electric field inside. Again, there are many details which I would love to talk to you about, but time is up. So in conclusion, some of us are having great fun doing this. If we're a bit lucky, we'll get some hints and maybe we'll contribute to changing our picture of the universe. And our hope always is, though there's no guarantee, that we contribute a bit to a revolution in our understanding of physical reality and hence a lot of unanticipated consequences and applications.
So first question is, how do you know that you don't have two or more particles in the trap at the same time? And how do you just let just one out?
Well, that's a good question. And I like to joke that in order to even know that our apparatus is turned on, because it's so precise, we have to make a more precise measurement than most physicists make in their whole career. Okay, so it takes a little time, but in the end, you can look, for example, at how the electron responds to electromagnetic forces that you apply to it. Suppose you take a little voltage and put it on these metal electrodes that are around the trap, okay, and you drive it and you look at where its response is biggest. And if you look at the width of that resonance curve, you know, it gets bigger when you're right on resonance, just like when you push your kid on a swing. Okay, the swing swings most when you're right in resonance with the natural oscillation frequency of the swing. If you look at how wide that response is, it gets twice as wide for 2 particles and 3 times as wide for 3 particles. There are other ways we can tell too, but that's one. Now, how do we get rid of, suppose we have 2 or 3 and we don't want that? Well, one way is we just turn up the juice, okay, on the drive, and we drive it so that these electrons get perilously close to the electrodes until one of them or more hit the electrode, and then and then there's only one left. Now, that's a little bit nerve-wracking when you do that. You know, when we used to have an antiproton in a trap at CERN and we couldn't get another antiproton for a couple of days, and suppose we had 3 in, then there was a lot of pressure on the students, okay, because you didn't want to dump 3, you wanted to dump only 2, okay, but you know, after a while you learn how to do it, and most of the time you could, well, in physics you often make your own luck, and that's what we were able to do. Did I answer the question?
I think you did. Yeah, that was very good. And what happens to a particle in the trap if it's chilled all the way to absolute zero?
Well, if it was chilled all the way to absolute zero, in those energy levels that I showed you, it would only occupy the lowest energy level, right? There would be no motion. But here's an interesting thing about quantum mechanics. Even though we don't cool nearly to absolute zero, but only to 1/10 of a degree above absolute zero, that's pretty chilly, okay? But even at that temperature, the particle is going to stay in its lowest state for more than 10 to the 30 some years, okay? So for all practical purposes, its cyclotron motion, this circular motion, has completely stopped already at the temperature that we do the experiment. And it stays in this ground state until we put some electromagnetic radiation, some microwaves, just like from a microwave oven, but higher in frequency. We put them into the trap and persuade the particle to jump from its ground state to its first excited state.
Okay. So how do you measure such small magnitudes accurately?
Well, it's challenging but fun. Okay. I think one important thing to realize is that you have to basically do it with ideas, not just fortitude and perseverance. Okay, you can't make order of magnitude improvements unless you have better ideas. So we use every quantum trick we can think of, or beg, borrow, or steal, as they say. Okay, and we invent some. We just have a paper out in Physical Review Letters a couple of days ago about a quantum detection back action circumvention method, for those of you who want to really get into the details there. But basically what we try and do is we try and arrange our experiment in such a way that we are sensitive to only what we're really interested in, and not and we try and measure that directly rather than measuring a very small effect on a very large quantity. Okay. Yeah, I don't know exactly how to explain that more accurately, so that probably will have to do.
Yeah, it's just probably a pretty complicated answer. So Are there galaxies far away maybe that are made out of antimatter?
Well, we kind of know about how big the universe is, and we can probe, we can, get some, see some effects of galaxies that are quite far away, right? That seem to span the size of our universe as we know it. And so far, we have failed to see any significant signature, say an annihilation signal from other galaxies. And one would expect that if there are galaxies made out of antimatter, galaxies are always colliding with each other somewhere in the universe all of the time. And we would expect to have seen some evidence of that. But when people have looked for that, even on satellites, to get more detection sensitivity with less atmosphere, they have failed to detect any evidence of that whatsoever.
Very unlikely. So how do you know that you've created antihydrogen and not hydrogen?
Well, that's actually pretty easy, okay? What we do these days is we hold it in a trap. It's a kind of magnetic trap that I didn't have time to talk about. But what we do is we hold it in the trap, and then we say, okay, we've held it for a while. Let's wait till there's no background of any sort from the accelerator, and let's just dump it out of the trap by removing the trapping fields, okay? And we'll let it hit the wall. And if we let it hit the wall, then it makes some garbage particles, I call them, called pions, which come screaming right out of our apparatus. We put up plastic scintillator plates, okay, and we see the annihilation signal. Now, there's no way that a proton could ever make such a signal. So it's entirely unambiguous.
That's cool. So are there antiphotons?
Well, maybe the photon is its own antiphoton. So some of these things, answers are yes, but by a technicality. Okay, so yes.
All right. Are you using any AI at Northwestern as part of your tabletop experiments?
Oh, hopefully not. We have enough trouble getting enough real intelligence, let alone making artificial intelligence. No, we really don't. Okay. Now, it's not that we wouldn't. If there was some place where a learning mechanism would actually help, and it would save us some time, and we could sleep while the computer was running the algorithm, that would be great. But most of our experiments are so delicately balanced that, again, we have to set up the apparatus following ideas that allow us to directly detect something, not just pick it out of a huge background. And so far the answer is no. But we would if there was a good reason for it, because they're perfectly valid and useful techniques.
Mm-hmm. So this person asked so if you had an unlimited budget, would you pursue further knowledge of dark matter is what they're interested in, but maybe I would broaden it to say, what would you do if you had,
Well, I guess I wouldn't want an unlimited budget, because I think an unlimited budget makes creativity go right out the window. So an unlimited budget is not adequate. Budgets are better than unlimited. We are doing a dark matter experiment right now in the Center for Fundamental Physics at Northwestern. All of the four principals, the four groups, are collaborating on this. And what we're doing is we're looking to see if a certain kind of dark matter comes through, whether or not, one effect of this dark matter would to take an optical cavity, two mirrors, and make the cavity change its size as the dark matter came through. And so we're comparing, we're just setting up the experiment, but we want to look for a length change of the cavity using laser techniques. And in order to, the problem, of course, is we need to compare that change in frequency to something. And the difficulty is if you compare it to a clock, there's going to be the size change in the clock as well. So the dark matter will change the clock. So you got to come up with a different way to tell whether or not there's been a change. So what we want to do is to suspend two mirrors and a second cavity, suspend them from very thin wires, very thin fibers. Okay, so if the dark matter comes through, the inertia of that cavity, okay, it won't respond right away. Okay, and so by comparing the length of that cavity with the rigid cavity, which can respond right away, much quicker anyway, then we can see whether some dark matter of a certain kind came through. So the answer is we would like to detect dark matter. And in our center, there are, we're trying to detect dark matter. There's molecular spectroscopy. There's gravitational experiments. There are searches for gravitational waves. We're interested in all that kind of stuff. What makes us a bit unique, though, is we try and do it on tabletop scales, okay, rather than on large facility scales, which means we don't need an unlimited budget.
Okay. So yeah, if you have a very huge budget, then you have to get in all kinds of people. It makes it very complicated, right? Like an LHC, for example.
At Fermilab, I mean, the Fermilab people are experts at managing a very large budget, but there's lots of organizational charts and software to do that, and we're blissfully spared most of that. So
yeah. So how about this one? Someone is saying, could a sister universe have formed along with ours such that the sister universe is all antimatter from our point of view?
I guess the answer is yes. I don't usually spend a lot of time thinking about that or talking about multiverses, because things which intrinsically can't be detected seem to me off the radar screen of at least this physicist. Okay. So I know that that's a lively theoretical speculation, and it gets a lot of interest in all these multiverses. As one theorist friend of mine who once said, and he had a Nobel Prize, so it's more respectable coming from him than from me. He said, multiverses are a sign of weakness. If you have to resort to a multiverse, you just fail to explain our own universe. But of course, there are really good and clever people who are looking into those ideas. I'm just not one of them.
Mm-hmm. So then a related question is, does antimatter's absence disprove the Big Bang Theory?
Well, physics is an empirical science, and in physics, we never say never. But on the other hand, I would say the odds seem really unlikely because there is so much evidence that a Big Bang happened. I think that I'm completely convinced at this point. So I would be absolutely floored if that weren't true. And we scientists, when we're always provisional about things, but that sort of empowers some people in our society to say weird things, that there's no climate change or, dumb stuff like that. Okay. And I think we have to be careful to say some of these things, the evidence is so overwhelming that, we really aren't provisional about it anymore. And for me, the Big Bang is in that category for sure.
Okay. Here's a question. I haven't heard of this. Have you heard of Wheeler's one electron universe idea?
No, I'll say no.
Okay, then we'll skip that question. If antimatter annihilates on contact with matter, how does that PET, the positron electron tomography scanning, work?
Well, the basic idea is if you eat something that has a radioactive nuclei in it that will emit positrons, say over the next several hours, okay, you can make such species, and you ingest this, and you ingest it if it's attached to a molecule that goes to an important place that you want to look at, say a brain tumor, for example, okay? Then what's going to happen is you're going to get positrons and electrons emitted at the same time, okay, from this, you're going to get positrons emitted, and when the positrons are emitted, they make gamma rays, they decay into the gamma particles, and they go in opposite directions, okay? And so if you have detectors on either side, you can extrapolate back to where most of the positrons came from. and you can then, with the right camera system, you can image what the where these photons, these light particles are coming from, okay, and that come from the positron annihilation that happens when a positron hits an electron in the material that it annihilates in. Very useful technique.
Mm-hmm. Here's another question about your technique. Do your observations affect the outcome? Does it affect, just observing it impact your system?
Well, the answer is yes. Now one has to be very careful. If you go, say, to our one electron or one positron system, and that's what the paper that just came out in Physical Review Letters is about, if you have a deep interest in this, okay? But we use a method called quantum non-demolition methods, called a quantum non-demolition method. And the basic idea is that when you first measure a quantum state of our electron, one of these levels that I showed you, well, let's not talk about the first measurement, okay? Let's talk about the second measurement. If I measure it again, it'll be in the same state that I measured after the first measurement. And if I measure it a third time, it'll again be in the same state, okay? So that measurement will not change the quantum state. So that's a valuable kind of measurement, because now I can do something on the side that I think maybe will change these states, like put some photons in to make an excitation. And if those photons don't make an excitation, I'll always measure the same state. My measurement itself won't change the state. So we use tricks like that a lot, okay? And so yes, if you don't take quantum mechanics seriously, quantum mechanics in general, if you don't design your measurement right, the measurement itself will mess up some of the things that you could be wanting to measure. All right, so it's very important to keep your quantum wits about you when you're doing these things.
Mm-hmm. If somebody's wondering if dark energy could be created by the annihilation of matter and antimatter, maybe even from microscopic black holes.
I doubt it.
Doubt it. We don't really know what a dark energy is coming from. Huh?
Yes, we know so little about dark energy. I mean, it's really incredible, I would say. I mean, we're a gazillion orders of magnitude away from being able to estimate what it should be, okay?
Yeah. So you were talking about all the symmetry. So someone asked, is there a negative of time? Is there like anti-time?
No, there's not. And clocks never run backwards, even though we talk about time reversal symmetry, okay? And so, I mean, if I have an equation that describes the motion of a car, let's say, okay? And so I could take a high school physics equation that describes the motion, something like a distance is velocity times time, right? Now, I could change the time variable in that equation to minus t. Now it would say that distance is minus the velocity of time. That would not describe the car that I was first describing. It would describe another car that was going the opposite direction, okay? And we say there's time reversal symmetry in that case, because both of those are possible motions of a car. But that's not to be confused that one car is moving in both of those directions at the same time, or it suddenly changes and goes the other direction. So when theorists talk about clocks running backwards, they're usually pulling your leg a little bit, okay? Though that's the way they think about it in their imaginations, okay? But in reality, it doesn't happen for us experimenters.
Mm-hmm. Okay, I'm just going to ask you two more questions. So, given that matter and antimatter particles exist, are the force carriers, the gluons, the photons, W and Z bosons, are they applicable to both matter and antimatter? Those aren't reversed?
Yes. Well, what's reversed? Let's just say that matter and antimatter particles are held together by gluons, okay? And then you have to sort of delve into the details more. Okay.
So there aren't like anti-gluons.
Yeah, well, it's sort of like with the photon. Okay, so yeah.
Uh-huh. Yeah. All right, so the last question is for the layperson, what's the most exciting recent discoveries in this area?
What is the most exciting recent discovery? Well, I think, for me, it was sitting in the lab when we last tried to measure whether the electron distribution was spherical or not. Okay, and we did something we call blinding. Okay, we took the measurements that we were doing and we deliberately put an offset on it so that we would analyze all of our data without knowing the answer. So we went through the whole process for several years, making this measurement and building the apparatus for 3 years before that. Okay, made a couple years worth of measurements, and we sat there with champagne and wine. Okay, some from France and some from California, right? And we sat there and we unblinded the result. And there, were we going to discover, that the electron wasn't spherical or it wasn't? And either result was okay with me, but it was kind of exciting to unblind the result and see what happened. Okay, so I mean, either we would discover this new physics going on, or we would disprove a lot of theoretical models. Either was fine by me, and I found it was kind of exciting.
What was the answer?
The answer was that we didn't see a departure from sphericalness, even though we had measured, well, twice we did this. We measured 10 times more accurately once, and then we did it again. And despite the 100-fold improvement, we did not see a departure from a spherical electron charge. Okay, and so far the standard model is right, but hope springs eternal. We hope that another order of magnitude is going to perhaps let us glimpse the first difference.
All right. So thank you so much for tonight. It's been very, very interesting. People, if want to, they can raise their hands again to thank you. So thank you very much.
Goodbye, all.